All right. Hi, everybody. Good evening from California this time. It's always been the morning, so we switched the time, and happy to see many of you made it. So today we have a presentation by Dr. Ashleigh Hood. Ashleigh, you can go ahead and start sharing your screen, actually, from the University of Melbourne. And just for an announcement, the rest of this year until through December, we're going to be having the VSPG at 5 p.m. Pacific time. And we'll revert back after the new year. And this is sort of experimental to see how this works, but we're trying this to try and increase the diversity of perspectives, get people who can give presentations while otherwise they would be sleeping when it's 8 o'clock here. So yeah, that's my only announcement, and I'm going to go ahead and introduce Ashleigh for us. Dr. Ashleigh Hood is a sedimentologist and geochemist with some of her key interests being Earth's atmospheric oxygenation, understanding Precambrian marine environments, Neoproterozoic snowball glaciations, and the boring or not so boring billion. Ashleigh received her bachelor's degree and PhD from the University of Melbourne with Professor Malcolm Wallace. Her thesis was Neoproterozoic seas, ocean chemistry, and marine carbonate mineralogy. After postdoctoral fellowships at the University of Melbourne and as a NASA Astrobiology Institute postdoctoral scholar at Yale, she's settled as faculty at the University of Melbourne, where she's currently senior lecturer in sedimentology. Ashleigh, we're really happy to have you here today, and please go ahead and take it away. And unmute yourself, sorry.
Thanks. Biggest faux pas of a Zoom meeting. So thanks, Alex. Thanks very much for inviting me along. I've been really following these talks and they've been really great. So I'm very excited to be part of this series. So today I'm going to be looking at, broadly looking at the Neoproterozoic carbonate record and what it can tell us about the environmental and climate change that happens during this time. So I'm a sedimentologist and dabble in geochemistry, and I look at these shallow marine carbonates in different shallow marine settings. And in this talk, I'm going to talk a little bit about these big glacial carbonates as well, to try and get a bit of an understanding of Neoproterozoic change. So the work that I'm going to be showing today is a little bit of a review, and that's just because I've gotten back from a year's worth of maternity leave, and you can possibly hear my kid crying. I'm just going to shut the door. So really this is a review and a bit of fieldwork, new fieldwork that we've done that's been done by the group that we've had at Melbourne and co-authors at Yale and collaborators that I've listed down the bottom here who've really contributed a lot to this talk. So kudos to them rather than me who's just showing it. So broadly, Earth's marine systems or marine evolution has been quite significant through time, particularly from the Phanerozoic, from the Precambrian into the Phanerozoic. With all of the different changes that have happened in the Earth, from the very early Earth to what the seawater that we have today, the composition has changed significantly. And I point this out because this is something that in carbonate sedimentology perhaps wasn't too widely kind of recognized, I'd say up until the last couple of decades. And so what I want to show in this talk is looking at tracking this seawater composition and tracking biological evolution in this seawater using the carbonate record. So I've taken this picture from Max Lechty's talk, who did the talk a couple of weeks ago, because he always has the most beautiful figures. But essentially this shows Precambrian atmospheric oxygenation, and many of you will be familiar with this type of diagram. This blue line here shows oxygen as a percent of present levels as we go from the Archean, very low levels, through the great oxidation event to kind of the mid-level Proterozoic, this sort of chaotic Neoproterozoic time where we think there's another oxygenation event, and then up into the present atmospheric oxygenation of the sort of Phanerozoic and today. And you can see Max has put in, or I've taken out of Max's figure, some sort of events in biological evolution as well to tie to this, and also many of you will be familiar with this, so I thought I'd just briefly include it. So the evolution of bacteria, photosynthesis, and the Archean, the evolution of eukaryotes, all of these sort of big changes in biological evolution tend to be broadly associated with this oxygenation history. In the Neoproterozoic, which will be the focus of this talk, we see not only changes in the composition of the biosphere and that concentration of oxygen, but we also see these two big ice ages, the Sturtian and Marinoan, that have been called snowball Earths, where potentially the whole Earth froze over. This is also when we see, of course, the evolution of animals around about this time, with the plus or minus of 100 million years or so of the Precambrian that I tend to talk in. So you can see that I think this oxygenation basically is one of the key processes in changing Earth's surface, and that includes Earth's oceans. So down the bottom here is a sort of cartoon of each aspect of this timeline. So this shows ocean chemistry as we go from the early Earth, the Archean, through the Proterozoic and into our sort of modern Phanerozoic oceans. And so associated, of course, with this low oxygen in the Archean, we see largely ferruginous or iron-rich and anoxic oceans in the Archean. The Proterozoic, we have a bit of a mix going on. So in the Neoproterozoic, you see, for example, some oxygenated upper oceans, some areas of euxenia, sulfide-rich, and some areas that are still, where the bottom oceans are still ferruginous, so iron-rich. And then at some point in the Phanerozoic, potentially quite a bit later than we still think, maybe in the Mesozoic even, our oceans became broadly oxidized. So along with this big change in marine chemistry, we also see a significant change in carbonate precipitation through time. And I think these two processes are very sort of tied in together. So in the Archean, in this early Earth system where we have widespread anoxia and perhaps microbial life, we see a lot of unusual type of carbonates. We see crystal cements, seafloor cements that precipitate from seawater. Perhaps the oceans were very alkaline. There's a lot of different literature on this. As we go through the Precambrian, with our biological evolution, we change in the frameworks of our carbonates. Because carbonates are often a biological product, we transition towards a sort of a more biological product with less of this cement. And into the Neoproterozoic, when we look at the reefs here, we see sort of Phanerozoic style frameworks where we have more complex life that makes up the framework of reefs, for example, or carbonate platforms. We see textures like marine cements. These are crystals that precipitate from seawater as you pump seawater through a platform margin, for example. Internal sediments, we see all of these features that are more characteristic of today's carbonate record. And of course, when we have the evolution of animals at some point during the late Neoproterozoic and into the Phanerozoic, we see these exquisitely preserved, beautiful carbonates. So I like to show this trilobite eye, which is made of a calcite lens. So these carbonates, I think, really nicely track this change in seawater chemistry through time. And this is what I've been interested in looking at over the last couple of years. One, I guess, problem with trying to interpret this record, problem in many people's eyes, I guess, has been termed the dolomite problem. And that refers to this change in the abundance of dolomite through time. So in the Precambrian, you can see here in this record put together by Marjorie Cantine, in light, we see a huge abundance of dolomite in our preserved carbonate record. When we go into the Phanerozoic, and here's just the Cambrian as an example, we see a lot more limestone in the record and not as much dolomite. So a much larger amount of this dark coloured limestone pops into the system. And this seesaw abundance of dolomite has been argued about for many decades now. And that's because the Phanerozoic, we don't see much evidence of dolomite in the record. And in today's oceans, we don't see much evidence of dolomite precipitating from seawater. And so it's been argued as to whether or not the abundance of dolomite in the Precambrian is a result of just these rocks being older and subject to more diagenesis, more burial, or is it a result of changing surface processes through time? And that's, I guess in this talk, I'm just going to give this away right now. This is what the angle I'm going to push. So tied into this evolution of the oceans, I think that this changes the type of carbonates that we're precipitating. So along with the actual abundance of dolomite, I think the type of dolomite changes significantly too. And so this has been documented by a number of different people, that in the Precambrian, we get these really beautiful fabric preserving or mimetic dolomites that retain all of the depositional features of the original carbonate rock. And so in this case, this is a Tonian sheet cavity from the De Vetta Formation. these are beautiful pendant microbes that you can see with several generations of marine cements, internal sediments, essentially anything you'd expect to see in a really well-preserved Phanerozoic rock, but it's all preserved as dolomite. And along with this beautiful mimetic dolomite, we also see evidence of primary dolomite precipitates. So these are marine cements that precipitated directly as dolomite from seawater. And I spent a large part of my PhD documenting these from Australia and Namibia. So a different type of dolomite that you see in the Phanerozoic. And I think this can be quite nicely shown by just looking at a single grain type and how dolomitisation of an original limestone would look. So here I've got ooid grains. This is from the Paleoproterozoic, MacArthur Basin. It's a calcite ooid that's been dolomitised, and you can see that the beautiful textures of this ooid grain have been preserved in this very, very fine mimetic dolomite. Whereas in the Devonian here in the Canning Basin, the same calcite ooid has been destructively dolomitised, and it's a very coarse texture that's destroyed all of this original depositional textures. And so this, I think, represents this fundamental change in the type of dolomite that we see. So that's, I guess, so I'm going to do this sort of broad introduction, and now I'm going to focus in on the Neoproterozoic, show you a little bit of sort of recent work we've done, and then I'm going to focus more onto the stratigraphy from Australia to look at some of these, some of the rocks around these big ice ages in the Neoproterozoic. So as a way of introduction into the Neoproterozoic through a carbonate lens, I think you can see big changes in the Neoproterozoic record via using carbonates. And I'm obviously trying to sell carbonates here. Hopefully I can do a good job. But the Neoproterozoic oxygenation event, which is here I've stolen again from Max's diagram, happens around about this time. You can see this record, I think, quite nicely in carbonates in things like the cerium anomaly record that we've put together, and also in things like iodine calcium in carbonates. These nicely show up this Neoproterozoic oxygenation. The evolution of animals during this time, or different types of life, can be often preserved in carbonates, not always, but things like biomineralization, the first biomineralizers in the late Ediacaran certainly are part of the record of reefs during this time. The snowball Earth, the kind of the theory that Paul Hoffman put together in 1998, I like to think is based largely on carbonates, on the carbon isotope record from the earlier and the following carbonates that surround these big glacial units. And I'm going to talk a little bit about the carbonates that we actually see within the snowball Earth glacial sediments themselves today. And then, so that'll be the first part of my talk. The second part will focus in on these cap carbonates, which are these unusual dolomite units which abruptly overlie the glacial sequences. And here's an example of one of these here, these buff-coloured thin dolomite units that have been are sort of seen as wildly strange or enigmatic carbonates. So, okay, so this is, it's a lot going on in this picture, but essentially this is one of these records of redox through the Neoproterozoic. And so focusing in now on this time, I wanted to just show this briefly. It's some work that Malcolm has put together that is going to be submitted that looks at the cerium anomaly record from the Neoproterozoic into the Paleozoic. And so the details of this, I guess, for the purposes of the talk are not that important, but essentially cerium is a redox sensitive rare earth, and it's removed from solution or removed comparing to the other rare earth elements when you have oxygen around. So a cerium anomaly or no cerium anomaly or number one suggests that there's no oxygen present, it's anoxic in the carbonate, which is sourcing it from the seawater. And as you move up on this graph towards, say, a Holocene carbonate value, you're moving towards more oxygenated conditions. So up is oxic and lower is anoxic. And this is just a lowest best fit through these data points. The green ones are data points from our marine cements that we've collected through this period of time, which we think preserve really nicely this seawater record. And the blue data are from all different other techniques that are available in literature that other people have put together. And you can see just broadly here that through most of the Neoproterozoic, we see sort of relatively low values, maybe with this one outlier here, up until around about the end of these glaciations. So we start to see more oxygen in this record, which points to a sort of an Ediacaran oxygenation event. And in the Cambrian, of course, and in the Paleozoic, we see still relatively reducing conditions, but probably more oxygen present than the Neoproterozoic. So this fits with these big records of oxygen through time. So along with this sort of oxygen, when we focus in on the Neoproterozoic, we can also use carbonates to look at the major ion composition of seawater. So I'm interested in the amount of magnesium that we see in seawater because this relates to dolomite precipitation. Dolomite, of course, is calcium magnesium carbonate. And one very simple way that we can get at this is just to look at these ooid grains again. So ooids have characteristic fabrics that can tell you about whether they were precipitated as aragonite with these tangential cortices or as calcite with these radial textures. And I've compiled this for Guang Yi's paper, which was published this year. And you can see that in grey are the aragonite ooids, and in sort of blue, which I guess overlies the grey a little bit, calcite ooids. And you can see from this record that essentially the Neoproterozoic is largely composed of aragonite grains. And this has been called aragonite seas. And these are very broad conditions that just really sort of link to tectonic or climate conditions very, very broadly. So they're not based on, I guess, individual, an individual ooid can't tell you much, but a number of different ooid-bearing strata can tell you broadly whether you're in one of these aragonite or calcite seas. And so the Neoproterozoic tends to be characterised by aragonite precipitation, which indicates high magnesium conditions, whereas the Cambrian, the later parts of the Neoproterozoic into the Cambrian, tend to be more calcite seas or tend to be dominated by more calcite precipitation. So high magnesium, possibly anoxic conditions in the Neoproterozoic. What about dolomite itself? So this is again just a compilation of these same ooids. Instead of looking at their original mineralogy, I'm looking at the way that they're preserved in the record. And so here again, the number of ooid-bearing strata through time, and I'm sorry, I'm flipping the axis back and forth with time, but in light grey here, you can see that most of the Neoproterozoic ooids are preserved as this fabric preserving dolomite. But when we get into the Cambrian, we see more of this blue limestone preservation and destructive dolomitisation. And so again, I think this is showing that this flip between abundant mimetic dolomite precipitation in the Neoproterozoic and more destructive precipitation in the Cambrian, which tends to be associated with diagenesis rather than marine conditions. Putting all of that sort of together by way of sort of characterising Neoproterozoic seawater, then these ooids and these carbonates have shown us that seawater is largely anoxic or, you know, at depth, probably ferruginous, largely in cases of many of these basins in Australia. We see high magnesium seawater conditions, and we see abundant mimetic dolomite and primary dolomite cements. So I think this kind of sets the stage for the type of carbonates that we see in this record that I'm going to go into in South Australia as a sort of context, as this type of carbonates that we might expect to see in this Neoproterozoic. So I'm going to zoom in now on the Adelaide Fold Belt in South Australia, the Flinders Ranges, where I've done a lot of work with Malcolm Wallace over the years and many of our students. And in this sort of stratigraphy through here, I'm going to go through the Sturtian glacials first. So this is the older of these big glaciations. I'm going to talk a little bit about these in orange, these unusual dolomite crusts or cap carbonates that we see in the sequence in Australia. And I'm going to talk a little bit about this change between, in yellow, mimetic dolomite into limestone as we go through this sequence. And hopefully with this context of this unusual so-called Neoproterozoic seawater that dolomitizes things being actually not so unusual when it comes down to it. So firstly, syn-glacial carbonates. So these big snowball earth glaciations in the Neoproterozoic are thought to be very, very severe. And under Paul Hoffman's theory in 1998, originally, they suggested that global ice cover would separate essentially the ocean and atmosphere. And the oceans then would become dominated by hydrothermal inputs with no continental input and no exchange with the atmosphere. And so in this case, these subglacial oceans, you might expect conditions where they're acidic, so you're dissolving carbonate from this hydrothermal exchange. You're oceans would be cold. Obviously, it's a very severe ice age, so you wouldn't expect much carbonate to precipitate, which is often found in warmer conditions. And also, you might expect to have relatively low concentrations of magnesiums in this seawater. And that's if, as magnesiums exchange with calcium in hydrothermal systems and mid-ocean ridges, the magnesium is sort of sucked out of seawater and put into the crust, and the calcium's exchanged and put into seawater. So these are some of the sort of ideas what you might suggest to find in the seawater of these glacial oceans. And a lot of work has been done over the years of this. I'm just taking this back to a very simple level. There's a lot more than we know about this now. So I want to focus in on this area, Hollowellina South, which is part of the Flinders Ranges near Hawker here in South Australia. And looking at some of the sedimentology of these Sturtian glacial sediments to get a bit of an understanding of how well this carbonate record within the glacials fits with a very, very severe ice age. And so in Hollowellina, Max Lechty has done a lot of work on these ironstones that he talked about a couple of weeks ago, and I encourage you to check out his video on YouTube. We also see, of course, a lot of glacial sediments like diamix through the sequence. But unusually, or perhaps not so unusually is what I'm going to say in this talk, we also see an abundance of carbonates, in this case dolomite. This actual picture has been taken from Orocorina, which is just slightly to the north of Hollowellina. But you can see in buff coloured here all these interbedded dolomites within the glacial sequence. So Hollowellina, zooming in here, is a station in South Australia, and we've done several sections through the glacial stratigraphy. So just by way of introduction, the lower part of the stratigraphy here is the Pualco-Tillite in blue. There's a Hollowellina ironstone, which is this red unit that overlies it, and above this, the Willioper Formation. And on the left here is the sort of representative strat sections that come from different parts of this sequence. The whole of the sequence itself is actually several kilometres thick. And you can see in yellow and kind of orange colours through the sequence that we actually see quite a lot of dolomite and dolomitic siltstones. So there is actually quite a lot of carbonate in this sequence, particularly in this kind of earlier Pualco-Tillite, that even the diamix are very carbonate rich. And as we go up through the Willioper Formation, we see a huge amount of different types of dolomite. This is an aster image of the same area. And so for context, the lower part is the Pualco, this kind of pinky coloured thing here is the Hollowellina ironstone, and then up until this dashed line is the Willioper Formation. So the colours here can be chosen from different bands of the aster satellite, and the colours essentially represent different mineralogies in this band combination that Malcolm's put together from this image. And in this case, the sort of bluey colours that you see under and above the ironstone represent carbonates, whereas the sort of pinky colours and yellowy colours up here tend to be more representative of clastic lithologies. And you can see that this large lower part of the glacial interval is characterised by very carbonate-rich lithologies and some interbedded carbonates in this upper sequence. So you can actually track this carbonate quite nicely, actually just using satellite data. But what does it look like in the field? So there are a number of different forms of dolomite within the Sturtian sequence itself. You get this unit, the Wokowi dolomite member, which is just above the ironstone, which looks like very much like a cap carbonate. There's a laminated dolomite sequence with graded beds. We see graded beds of dolomite as well. This kind of orangey coloured rock here is dolomite within the Willioper. We see that these beds are deformed by sedimentary processes that suggest that the dolomite had precipitated relatively early. So this is a dropstone emplacement. And also the dolomite forms the matrix of many of the diamix and tills through this area. Out of the beds that we picked, the carbonate content is quite high in a lot of cases, so an average of about 40% and up to about 70% dolomite for these sort of beds that we targeted for this analysis. And when you look at this dolomite under thin section and under SEM, you can see that it's characterised often by euhedral or subhedral crystals, which show some zonation. So no evidence really of a detrital core, which you might expect if this was reworked carbonates from the underlying glacials. And instead we think that along with this evidence of syn-sedimentary deformation, that this dolomite is occurring very early. Essentially, it's been precipitated at the sediment-water interface or just below as a sort of an Authigenic carbonate. So we think this dolomite's precipitating from syn-glacial seawater. Another sort of line of evidence, I guess, for these dolomites that form within the Sturtian being authigenic or precipitating from syn-glacial seawater rather than detrital, which was sort of a commonly held hypothesis about a lot of the carbonate in these glacials, is the carbon and oxygen isotope composition. So there's a lot going on in here, which I apologise, but in grey, in these grey diamonds, which largely plot over to the heavy side of this scale, are the underlying carbonates. So these are the Burrow group mainly, dolomites, and you can see they plot with relatively heavy carbon and relatively heavy oxygen values. The warm colours over here include some of the data from our study, as well as some other studies that have looked at dolomite within the glacials themselves. And you can see that these plot much lighter on the oxygen scale and much lighter on the carbon scale. And I would argue they plot distinctly differently from these underlying carbonates, suggesting that these are not detrital, they're not derived from the underlying erosion of these rocks. In the 90s, actually, Crossing and Gostin did a study where they looked at clasts within the diamictites as well, and they found that these clasts, which were clearly detrital in the tillites, fit in with these underlying Burrow group carbonates really nicely. So I think this is nice evidence that these carbonates are actually precipitating during glaciation. These are not reworked carbonates. And actually, these are found in a lot of different sequences over the world. So here's just some examples. So Ashleigh and Malcolm looked at these in Death Valley. Again, this kind of buff-coloured is dolomite, nodular dolomites and graded beds of dolomite within the Kingston Peak Formation. In Svalbard and in Scotland, you also see these as nodules and beds. And recently, there's been more work by Tyler Mackey on some of these Svalbard carbonates. But essentially, there's not an insignificant amount of dolomite within this Sturtian sequence. So how does this fit together then? It appears from the sedimentological data and from this geochemical data that carbonates are not dissolving under these sort of syn-glacial ocean conditions. They're instead precipitating. The occurrence of these dolomite beds, which is a calcium-magnesium carbonate, to me suggests that you need to maintain some sort of magnesium concentrations in seawater through this very long 50 million year Sturtian glaciation, instead of removing all of this magnesium into these hydrothermal ridge systems. So to explain this, I'm suggesting that we need a source of alkalinity into these oceans that is also providing a source of magnesium. And I think the most obvious and easiest source of that is continental weathering. So Don Penman, this is, I guess, a simplified version of Don Penman's work from our 2021 paper in geobiology, where he modelled the Sturtian glaciation using the precocious model of Penman-Rooney 2019. And the upper panel looks at carbonate saturation, in the lower panel magnesium concentrations as we go through a long glaciation. So there's two scenarios here. So I'm going to talk about the orange one first, which is this orange line and the kind of yellow glacial period. And then I'm talking about the blue situation that we think is representing the carbonate that we see in the sequence. So under the sort of very, very severe snowball conditions where you'd have no input of continental weathering into the oceans, or very limited, high deglaciation threshold where you need quite a lot of carbon dioxide to overcome these glacial conditions. In orange here, you can see that the saturation state of carbonate drops essentially to zero. We don't see any evidence of carbonates precipitating. And we see it pop back up again when we finish the glaciation and we precipitate the cap carbonate. And in this situation, in orange and magnesium, we drop to really, really low magnesium conditions as we go through this very long glaciation. And so this sort of scenario is inconsistent, very, very simply based on this model, which is, of course, it's a model itself, and there are a lot of different parameters that models do and do not take into account. But in this case, this no weathering scenario doesn't really fit, I think, with the precipitation of dolomite that we see in the record. Whereas a small amount of continental weathering, because this is undeniably a very severe ice age, so about 9% of current continental weathering is able to maintain, in blue here, carbonate saturation through the glaciation, and accounts for the cap carbonate when you finish the glaciation as well. And when you look at magnesium concentrations, we don't see any decline in magnesium through the glaciation either. So we suggested that basically a small amount of continental weathering, perhaps a small amount of open ocean, or a small amount of less extreme glacial conditions, I guess, can account for the record that we see preserved in South Australia. So that's the glacials themselves and the carbonate within them in the context of this Neoproterozoic seawater, which tends to be magnesium rich and anoxic. I think that sort of fits with the story so far. But what about these unusual cap carbonate units that overlie the glacials? This is an example from Mount Chambers Gorge in the Flinders Ranges, where we have the upper glaciation now, so the Marinoan sediments here in pink, and very sharply overlying them, we have this buff-coloured dolomite cap carbonate. This is from Joe Fale's thesis in 2014. So by way of, I guess, introduction to these unusual cap carbonate units, these are very distinctive, as I mentioned, thin, so only up to, say, 20 or so meters thick, generally dolomite units that directly overlie the snowball-esque glaciations. So here, again, in Namibia, this is the Gaub glaciation in this kind of bluey limestone colour, and then the cap carbonate on top of it. Actually, it starts up here somewhere. And so they have been, it's sort of enigmatic, I guess, to get a carbonate, which is generally thought to be a sort of tropical rock, straight after a glacial or cold rock. And people have been looking at these for many, many decades now to try and figure out how they formed. And there's a lot of very unusual conditions suggested for their formation, including in the aftermath of these big glaciations, including things like giant storms, super greenhouse conditions, intense ocean stratification. And they've got a lot of sort of sedimentological features and geochemical characteristics that are quite unusual that have led to these different theories. The geochemical composition of the caps is often characterised by this negative carbon isotope excursion. So here again, the two sections from Namibia, from Paul's work and from Simone Caseman, and you can see that the cap carbonates start off as with this kind of -5 signature, and they recover, you can probably see it here, they recover up to slightly towards 0 as you go through the overlying carbonates, cap carbonate right at the bottom here. So a distinctive negative carbon isotope excursion. This is again thought to be due to the severity of the glaciation during this time. In terms of sedimentology, these are also very unusual. So they directly overlie these glacial sediments. They generally have quite a sharp contact, although it can be slightly gradational. They're usually composed of dolomite. Sometimes you get some limestone ones, but generally it's dolomite composition. They have structures which have been called either teepees or giant wave ripples, which you can see in these sections here. This is from the Enorama Creek in the Flinders and from Namibia. So here's these teepees again. We get unusual sheet cracks, which are bedding parallel cavities that open up, and they have at the base, often at the base of these caps, and they can have dolomite cements in them as well. At the top of these units, we sort of grade out of the dolomite and it goes into a nodular dolomite in the shale. And in some cases, in Namibia, for example, you get aragonite fans and some other places barite at the top of, as you transition out of the dolomite unit into the overlying limestones. In these cases, you get these unusual aragonite and barite minerals. And so as I say, very unusual in terms of the general carbonates you'd see in any record. But what I want to show you now in this last little bit of the talk is that perhaps these cap carbonates are not so unusual in the schemes of Neoproterozoic seawater conditions. So here's the Sturtian. So again, the Sturtian glaciations, the Sturtian cap, the interglacial sequence, the Marinoan glacials, the Marinoan cap. And in these kind of pink colours, I'm showing a whole range of different units through the stratigraphy that resemble, in many ways, these cap carbonates. And I'm just going to go through and show you some of these and then tell you about what we think might be the reason for this abundance of sort of unusual dolomite crusts through the Neoproterozoic of Australia. So focusing first on the Knuckalina, so this Marinoan cap carbonate, which is the most distinctive of the different carbonates. Again, here's Joe's section through this at Enorama Creek. You see there's a sort of relatively sharp but somewhat gradual transition from this kind of pinky shale into the dolomite. These features here, which we suggest are teepees or expansion features related to the dolomite precipitation itself. Some of these you can see little eroded tops on them in this location, and nodular at the top. So these pinky dolomites within the red shales. When you look at these in detail, they actually have really interesting textures within them. So in the field, you can kind of see it. Here is a change in colour in these little graded beds, which are several, maybe a centimetre thick or so each, that make up this sort of 10 to 20 metre thick carbonate unit. So each of these beds goes from a shale, so in darker colours, up to lighter colours, turns into a dolomite. You can see this probably nicely in thin sections. So a shale transitioning up into a more pure dolomite as you go up through each one of these little centimetre scale graded beds. And often the next bed on top of it that also goes from shale up into dolomite forms a little erosion surface. And so we suggest these are actually little turbidite sequences. And each little sequence that comes down is eroding into the previous little bed of the carbonate. And if this is the case, then what we think is happening is that this dolomite is precipitating very early, essentially during sedimentation, for it to be then eroded by a subsequent turbidite flow. And so this sets up the idea that in this cap carbonate, dolomite is actually precipitating orthogenically sediment water interface, and it's replacing shale in each one of these little tiny graded bed units. And actually we see evidence for orthogenic dolomite precipitation in these kind of TP structures, where you see expansion related to the precipitation of the carbonate, which breaks up the beds and pushes them upwards. And we see these thin layers of dolomite cement as well, which coat some of these TPs. Again, suggesting that this dolomite precipitation is occurring very early during sedimentation. So that's the Marinoan. That's probably the most distinctive of these caps, but there's a whole bunch of other ones. And now I'm going to focus in on one part of the Flinders Ranges where we can see these unusual dolomite crusts within the interglacial stratigraphy of the Flinders. So these come from a place called Mount Lyndhurst, which is up here in the northwest of the area. And Emily Horden did her, and Tessa O'Hare did their theses there in 2012 and 13. And so the stratigraphy here goes from the top right to the bottom left. So the Sturtian glacials, the Sturtian cap, this big thick basinal shale sequence, Tapley Hill, Enorama and Yankonina formations. And there's two big unconformities in this sequence. You can sort of see them here from this interpreted map cutting into the stratigraphy. And there's actually these dolomite units exist, the cap, and then there's one unusual dolomite unit in the middle of this big shale Tapley Hill formation, and there's two dolomite crusts that exist on these two big unconformity surfaces. This is what the Tapley Hill, so this bottom sort of middle of the basinal shale unit looks like in the field. So it's in the middle of this really poorly outcropping shale. You see this big thick unit that goes all the way for kilometres of stratigraphy laterally. And it, when you look at it, is characterised by these same graded beds that you see in the Marinoan. So in dark here, shale up into buff coloured dolomite. And there's this whole sequence of these in this unit itself. It has expansion features like TPs. You see nodular carbonates, you see sheet cracks developing, you see intraclasts, which are reworked this carbonate. Again, all of these features suggest very early orthogenic dolomite precipitation occurring at the sediment water interface. And interestingly, this sort of unusual unit as well, not associated with glaciation, also has the same sort of distinctive negative carbon isotope excursion in it. So very, very unusual. And as we go up, I'm just going to show you now the dolomites that form on these two unconformity crusts. This is what they look like in the field. So you can trace the unconformity on the air photos, but when you get up close, you can see the difference between the beds from the underlying shales and the overlying shales, which you can't really see very well in this photo. But essentially, these shales are cut by the unconformity at an angle, and you can actually see this angle changing as you get closer and closer to the top of the unconformity surface. So these beds are bending as you go upwards, and they actually change in angle by up to 30 degrees. The beds themselves at the top in this buff color have been essentially dolomite that's replaced this underlying shale, these basional shales of the Flinders. So as you go up these beds, you get more and more carbonate rich, more and more dolomite, you see more expansion, and you see a thickness in the state of the beds as well. And this, again, we think this suggests that this dolomite is precipitating orthogenically. It's precipitating on this surface, perhaps because it's an erosion surface and there's no sediment that's being put on top of it, sort of similar to those little turbidites that I was showing earlier. And this, yeah, essentially this dolomite is precipitating because of this lack of sedimentation and because of this Neoproterozoic seawater, which allows dolomite to precipitate fairly easily. So again, this is a thin section, I should say, as we go up from the shale into this dolomite crust. We go from a shale-looking dolomitic shale up into almost a pure dolomite. And this goes from D, C, B, A. You can see we get more and more of this high birefringent carbonate. So we can see this in thin section. And nicely in thin section and SEM, you can see actually this high birefringent dolomite is actually sort of eating into the clastic grains. So here it's embaying some of the quartz grains, it's eating into micas and clays, and suggesting that this dolomite is orthogenically precipitating at the expense of essentially whatever is sitting on the seafloor. So it doesn't just turn limestone into dolomite, it's also turning shale into dolomite as well. Just quickly now, so that was sort of this interglacial dolomite crusts, and we've looked at this Marinoan cap. I just want to quickly show you a couple of other images from one of these units in the Ediacaran, the wearing dolomite, and also some of them from the Sturtian that we've looked at more recently. The wearing dolomite up in the Ediacaran is supposedly, is potentially, I guess, related to the Gasquier's glaciation in a type of a cap unit. This has not been really formally associated, I guess, but again, we see it as these dolomite beds with intraclasts and graded beds here again from shale and darker up into dolomite in lighter colours, which very much resemble these sort of cap carbonate units. So it's possible that the wearing dolomite does represent some sort of a cap after the Gasquier's glaciation. Back down into the Sturtian, where we sort of started the talk, this Warcowie dolomite member that I mentioned, again, is graded from a shale up into a dolomite at the top. And in some areas, this can be up to 20 or 60 even meters thick, and sort of very much resembles the cap carbonate. And so this is one big unit that you get within the Sturtian, but also in the Sturtian further north, up towards Yankonina, you also get a huge array of dolomite beds, again here in buff colours, that exist all the way through the Sturtian stratigraphy, which are very similar in characteristic to a lot of these other dolomite crusts. And actually right at the top at Yankonina, right at the top of the Sturtian cap carbonate, which is not often very well developed, is quite nice. And you can see, I've probably got some ants for scale here. Unfortunately, I didn't realise that on a fly, classic Australia. But you can see as you go from the glacials here in this kind of dark shale and the overlying cap carbonate, you actually get some dropstones and glacial debris in the cap itself. And this is a sequence that's repeated, where you get repeated deposition of diamictite, dropstones, and then and dolomite in a series of kind of mini caps as you go out of the Sturtian in this area. And this, I think, is potentially interesting look at maybe a prolonged deglaciation in this particular part of the Flinders Ranges. But essentially all of these features put together, all of these cap carbonate-like units or dolomite crusts that are through the Flinders, we suggest can be very sort of simply explained by just being hardgrounds in a sense. So these features seem to be all associated with events that have sediment starvation, so lack of deposition, things like big transgressions like you'd expect after glaciation, and on things like unconformities where you're stripping away sediment and you're not adding any sediment in. So in the Phanerozoic, we recognise hardgrounds or these hyadal surfaces because they've got things like iron manganese crusts on them, they've got burrows, they've got glauconite, phosphatized grains. These are all characteristic things that you'd recognise in the Phanerozoic, where you have oxic seawater and you're able to precipitate oxides and you have life that's, obviously burrowing into these surfaces. But in the Neoproterozoic, where we have this magnesium-rich, anoxic seawater where we're precipitating dolomite, we suggest that these crusts are the type of hard grounds or hydal surfaces that you would see very commonly, and that we do see commonly through the South Australian stratigraphy. And in this case, these are associated with these dolomite crusts on graded beds where we see authigenic precipitation at the sediment-water interface, sheet cracks, dolomite cements within the cracks, and the TPs. These are all expansion features related to this dolomitisation. And the fact that we see reworking and intraclass of this dolomite suggests that it's happening quite early. And so I guess what I wanted to come back to at the end of the talk now is to just say that this, I think, relates back to this dolomite problem. These hard grounds, these Neoproterozoic carbonates are in fact not very unusual in the context of the Neoproterozoic and maybe the whole Precambrian. These are characteristic carbonates that you'd expect to find in anoxic seawater with high magnesium conditions, where you see abundant dolomite precipitation of all different types, including these hard grounds and cap carbonates in the sequence where you have events of sediment starvation, and you allow this seawater to interact with the underlying lithologies for a longer period of time. So then the demise of these kind of conditions can be also tracked, or I think very nicely linked to this marine oxygenation in this Neoproterozoic oxygenation event. And so you can see in the record in yellow is mimetic dolomite, and that sort of ends around about the interglacial Cryogenian, where the record is then green, preserved in limestone. And you get a couple of these little crusts that exist beyond this transition. But I think this represents a fundamental change in this sequence. And you can see, coming back to this serum anomaly work, that again, here being low oxygen conditions, and up further on the graph being more oxygen rich conditions in the sea water, that we go from low oxygen conditions, and as soon as we get into the sort of interglacial Cryogenian, we start to get more oxygen rich. And I think this nicely picks up this same signal in the carbonate record of the Flinders Ranges. And one way that I've been looking at this recently, and perhaps poorly explained recently in a GSA talk, is this coming back to this dolomite problem. Is it depositional or is it diagenetic? And I think it's a problem of perspective. So in the Phanerozoic, we see mainly oxic seawater, and we see these chemical zones that exist in these deeper areas where you might expect dolomite to precipitate. These occur in burial diagenesis, or burial of the sediments in the Phanerozoic, where our seawater is oxic. And so this sediment water interface is up here, and this is the perspective that we're coming from. But in our low oxygen world of the Neoproterozoic, these chemical zones actually extend up into the water column. And our sediment water interface, could be anywhere down here, and roughly I've just put this in little dolomite precipitating here. But essentially, I think this nicely explains how you can precipitate dolomite from seawater or at the sediment water interface, and perhaps why this argument has persisted for so long as to why there is a distinction between this diagenetic or depositional origin of dolomite. So just then to finish up, I hope that I showed that I think this marine dolomite precipitation and cap carbonate-like units appear to be very widespread, even through glaciation. This is a characteristic signal of Neoproterozoic seawater. Then there's protracted changes in seawater composition, and this decline of dolomite really relate to oxygenation in whichever ways that it contributes to the change in seawater composition. And so therefore, this dolomite problem overall, I think, is one of environmental change. And so I'll finish there. I'll just say thanks very much to all my funding sources. Thanks very much to my husband and my family and my kid, who was recently, turns out, not very good at measuring strat sections on fieldwork. But hopefully he'll be a geologist of the future. And I will end there. Thanks very much.
Thanks, Ashleigh. That was really good. We're going to go ahead and transition to our discussion session. I have a question in the chat that was sent directly to me that I'll ask first, but just to go over it, you can ask yourself, or you can ask a question by just typing into the chat, and I'll read it for you. But if you'd like to ask yourself, please just locate that raise hand button in the bottom. If you go along the bottom bar, you find reactions to your right. Raise hand is that very bottom button there. So the first one we have for you actually is from case under star one. Says, can the this is about the cerium anomaly graph through time. Can the Ediacaran outlier in the cerium anomaly graph be a consequence of the presence of bilaterians or any other such biological taxa? Follow up on this question. Are there any novel biological processes that are predicted by molecular clocks that have coincided with the cerium anomaly?
So I guess I haven't looked into that in so much detail, the actual direct links to biology. I guess we've probably only looked at it broadly through the redox itself, rather than trying to think of the reasoning for it. It's possible that this is when you see, I guess, the Ediacaran fauna evolve, and this is when you see a lot of changes in, for example, biomineralization and stuff like that. So it's possible that there's a link there. As to what the control is or what the direct link is, I'm probably less qualified than many other people here to comment on. So I might just leave that one open, but thanks very much for the question.
Okay, our first hand up in the audience is Greg Vitalik. Please unmute yourself and ask a question.
Hi, Ashleigh, that was really great. I was very interested in your account of the carbonates, that they all seem to be inversely graded. You went from shale up into coarser material. You didn't talk too much about the texture of the coarse material. You think that's a primary precipitate like the material below? How do you explain inverse grading, which seemed to be ubiquitous in just about everything you showed for the carbonates, at least?
Yeah, that's right. So the inverse grading, I guess, maybe I did a poor job of explaining this, but essentially what we think is happening is that the underlying lithology is a shale in this case. It could be a limestone in other cases. But as soon as you expose that surface to seawater for a prolonged period of time, at the sediment water interface and downwards from that interface, you start to precipitate dolomite as an orthogenic precipitate in situ. And the dolomite's precipitating sort of both in pore space and at the expense of the minerals that exist there. And so that's why we think that you get the sequence from most carbonate rich at the surface, which would have been the original seawater surface, and less carbonate rich as you go down. And then the little sort of erosion surfaces, or the fact that you're reworking that carbonate, then suggests the kind of timing of it. So it's quite early. It's essentially syn-depositional. And so that's, I guess, what we think is happening in each one of these ones.
I've looked at those rocks too, and they seem to be granular to me. They did not appear to be primary precipitates.
Yeah, I think in some parts
of
the world,
micritic. Yeah, very fine.
Yeah. Yep. So often you get little rounded kind of bits of dolomite, and again, these appear to be little reworked grains as they go down the hill. And in some places, you do get all sorts of different carbonates. So this is not necessarily, the case for all of these carbonates, but certainly in the Knucklina, Joe Fayle did a lot of work during his thesis. When he looked at it, he looked in hundreds of different thin sections and found this kind of characteristic sequence of the sequence in Australia. But yep.
And always coarsening upwards. That's weird.
Well, not necessarily coarsening upwards. So the bed itself doesn't change in grain size necessarily. It's just the amount of carbonate present is the gradational feature.
Okay. Yeah. Thanks.
Okay, next up is Brian Pratt. Please go ahead and unmute yourself. Brian, we can't hear you. Let's see if I can find. I just sent you a ping to unmute if you're struggling with it. Okay, Brian? You're unmuted now, Brian.
Yeah. I'm trying to figure out how to make my comment here. Alex, can you hear what I'm saying?
Yes, we can hear you.
Okay, so Ashleigh, my question is what is the buff color in both these things in the Well, in both these ediacaran units, is that due to iron enrichment? And if so, can you explain that, by the way?
Yeah, the buff color of the dolomite, I guess it's what the dolomite often looks like in the Flinders Ranges, and I guess in several other places, it's got to do with the iron, I guess, weathering out of it, essentially. Yep. Okay,
so here's a second question, is that if you look at the Miocene of the Mediterranean, the petrographically, the carbonates are like super, super mimetic, and we wouldn't think that the Miocene would be related to seawater chemistry. We would just think it, is some kind of like perhaps brines and so forth that have penetrated the carbonates. Do you have any comments on that kind of stuff?
Yeah, so I guess you do see some mimetic dolomite in the Phanerozoic in very sort of isolated places. The Miocene is one of them. I think the Triassic has got a few areas where you see mimetic dolomite as well, but very, very uncommonly. And so I guess I'm not necessarily saying that you go to zero. There seems to be a gradual decline, but the conditions under which you precipitate dolomite appear to be much more limited. And whether that's related to these periods of time having a different carbonate chemistry, or certain amounts of anoxia or iron-rich or magnesium-rich conditions, I guess I'm probably not necessarily qualified to look at each one of these in the Phanerozoic, because I haven't looked at them in too much detail. But it could be that certain aspects of these common Precambrian conditions are part of these particular ocean basins during these periods of time, like the Triassic, where you have the extinction of, just after the extinction of all these animals, you go back to normal.
Okay. All right. Thanks. We're going to talk about that.
All right. We have one in the chat from Masha Prokopenko. What do you think is the connection between the lack of O2 and precipitation of dolomite? Are you invoking the lack of sulfate, often considered to be an inhibitor of dolomite precipitation? Yeah,
so that's a really good question, and that's something we've been, puzzling over, and I think a lot of people have been puzzling over for many years. The connection seems fairly straightforward as to the exact conditions that initiate the dolomite precipitation. I think it's a mix of different things. So I think actually the biggest part of it is the magnesium in seawater. So you just need a lot of magnesium around to be able to easily precipitate dolomite, to dehydrate it, dehydrate the magnesium, to have just sort of abundant. So I think that's actually probably the most important factor. But then the anoxia seems to play a role in this as well. So there could be that the anoxia is promoting a range of different microbial metabolisms that, these microbes live in, for places like these reefs, for example, where you get dolomite cements, and the metabolism or the EPS generated, the organic matter generated through Precambrian ecosystems could be contributing directly in the metabolism, but also in the concentration of organic matter potentially. It could be the chemistry of the seawater itself. So as you say, the lack of sulfate or the amount of sulfide, or all of these different aspects. It could be the change in major element cycling that you get under different redox conditions changes a lot of these other factors, carbonate saturation. So I think that's a fairly broad answer with no real answer given, but a range of different controls that contribute.
Yep.
Okay. Next, Paul, you have Shuhai. Sorry, Shuhai had his hand up next. You're up, Shuhai.
Hi, Ash. Thanks for the great talk. I was intrigued. You mentioned dolomite replacing the shale, and I wonder whether you can say something about the pore water chemistry. What kind of chemistry would promote the dissolution of quartz and simultaneously precipitate dolomite?
Yeah, that's right. So I think I'm gonna I'm going to blame my year off on maternity leave for this, but I'm pretty sure I remember it being alkaline conditions where you get the dissolution of quartz, for example. But in terms of the pore water chemistry question, I think that the fluid that's doing this dolomitizing is essentially seawater. And when we're thinking of Precambrian seawater, we're not thinking of these chemical zones being very directly and very quickly changing as you go under the sediment water interface. I think these chemical zones are much more extended. And so something like ferruginous conditions, ferruginous seawater, is not going to abruptly change as you transition into the pore waters, only a centimetre or two underneath the sediment water interface. So I think actually it's the seawater itself that's barely modified. In pore waters, it's precipitating this dolomite, and potentially it's very, very alkaline, and that's contributing to the dissolution. I will note though that it has been a while since I looked at this, and so I'm interested to follow up further and chat with you if you wanted to chat.
Okay, thank you very much.
Great, thanks, Shuhai. Paul, you're up next.
Yeah, I'd like to clarify a couple of things about what was said in the 1998 science paper on Snowball Earth, because I think it bears on the source of magnesium to the Snowball Ocean, among other things. I'd also like to make a comment or two about cap carbonates and their significance and character. But first, the 98 paper, we certainly did not say that continental weathering was cut off and that carbonate saturation dropped well below unity. Quite the opposite. We maintained in that paper quite explicitly that carbonate saturation was maintained at unity during the glaciation by buffering, by carbonate dissolution. And of course, the source of that carbonate that was being dissolved was glacial abrasion, particularly abrasion of carbonate shelves and platforms, which injected the seawater continuously with rock powder. After all, the Maranoan glacial sequence in Namibia is 100% carbonate, mostly detrital. So there's lots of carbonate coming in. And so that helps to explain the magnesium. The most obvious source of magnesium to the Snowball Ocean would be abrasion of dolomite, of pre-existing dolomite, because after all, the cold temperature helps to dissolve the dolomite, whereas it inhibits the weathering of magnesium silicate. Okay, so I'd like to make that clarification. That we assumed in that model that carbonate saturation was maintained, because otherwise it's very difficult to account for cap carbonates through carbonate dissolution from glacial abrasion and injection. Now, I think the point about cap carbonates is less about how special they are lithologically as it is about their occurrence in places where you wouldn't expect to see carbonate. And in particular, in the very acidic environment that must have existed in the immediate snowball aftermath, because you need very high CO2 atmospheric concentrations to overcome the high albedo. And so this should have been a very low pH environment. So it's difficult to account other than with this buffering and extreme warming, why you would have cap carbonates at all. And so, moreover, when you plot the distribution of cap carbonates on most people's paleogeographic maps of the Cryogenian or the early Ediacaran, you find that the cap carbonates extend well into the mid-latitudes, which you don't normally expect to see for non-skeletal carbonate, because carbonates form preferentially in the warmest parts of the ocean at latitudes less than 35 degrees. So that also makes cap carbonates unusual and points to a very high degree, an anomalous degree of carbonate oversaturation at that time. And lastly, a very common, particularly in the Maranoan texture, in the Maranoan cap dolomites are these size-sorted peloids. In fact, it's the grading and the reverse grading of these peloids, which actually defines the lamination, which is strongly present in most Maranoan cap carbonates. So that's really a granular texture. I think that you can't really think of that as a hard ground, in addition to the presence of of low angle cross stratification and giant wave ripples and things like that, which confirm that these were granular deposits. Although I grant you the tubestone stromatolites could be considered a form of hard ground, although the tubestone stromatolites are, as far as I'm aware, are perhaps unique to the Maranoan cap dolostones.
Yeah, thanks, Paul. Yeah, no, that's a series of good points. And, you know, for the purposes of the talk, obviously, I oversimplified the 1998 paper. So my apologies for sort of not going into all of the reasoning behind that. But I guess based on a lot of the modeling studies that followed as well, that followed that original hypothesis, you know, a lot of them suggest that a lot of carbonate was dissolved. I think that Pierre Humbert paper from 2004 suggested that you would need to sort of remove, dissolve to buffer the oceans, as you say. You need to dissolve a lot of carbonate within those glaciations over many years.
In the 98 paper, we estimated that the amount of carbonate that you would need to dissolve, and after all, this carbonate, detrital carbonate, still there, so obviously it wasn't all removed. There was ample carbonate available for dissolution, but it would be enough to when it comes back out again after the glaciation, to cover the entire continental area with 3 to 5 meters of carbonate. So yeah,
I guess what we're sort of saying again in a simplified term is that it's just is it unusual that you do see this carbonate that seems to be precipitating during the glaciations? It's sort of contrary to what you might expect, you know, based on your paper, but also based on just what you think just generally about, you know, ice age. It is sort of seemingly unusual. And I guess the point that we're trying to make is that potentially it's just showing you the processes that are going on clearly, and you know, it needs further work. This carbonate stuff, we only just started looking at it really, but I think there's a huge amount of information you could pull out from these carbonate units to look at this syn-glacial seawater chemistry, and what it can tell you about the ice age. I think also is really interesting, and you know, seeing it all the way through the Sturtian for 50 million years, and seeing it in this kind of gradual transition now that from our recent fieldwork at the top of the Sturtian, to me suggests that the Sturtian at least is a very different beast from, for example, from the Maranoan. And so, you know, you're right, there's a lot more that needs to be done to be pulled out and looked at this, but I think it's a really interesting sort of new angle to take to look at these glaciations. I just wanted to also comment briefly on the your mention about the caps. Also, I think someone else mentioned this as well about the granular textures. So in some of the other cap carbonates around the world, you do see that granular texture with the sort of they look like reworked grains rather than piloids to me of dolomite. But this is not, I guess this is not inconsistent with the scenario that we're presenting as well. So in the sequence of Flinders, you don't really see these reworked grains defining grading. You can see little reworked sort of intraclass within each of the cap sequences, and bigger ones as well, but microscopic ones too. And we think these are again related to the fact that you're forming this authigenic dolomite and reworking it as the cap is being formed. And so I don't think that these granular textures are inconsistent with the idea of it this being representing a transgression as well.
I don't think the peloids are intraclass, and in fact, intraclass are quite rare in Maranoan cap dolomites, probably because of rapid accumulation. I'd like to make a couple of points about the authigenic syn-glacial dolomite. I can easily account for the negative carbon isotopes in those fine-grained dolomites. That's the Garvelach anomaly, which was poorly lithified and therefore easily converted into very, very fine-grained detrital material. And of course, it's no longer present in the source area because it was eroded. And that's why that detrital component, as I would argue, is different from the existing source areas, because the Garvelach, which you're missing in Australia, is in the Sturtian glacial.
I guess that again, though, it's a pretty short period of time as opposed to the extent of time that the Ternary carbonates represent that underlie the glaciation.
It was the carbonate that was at the surface at the time of the glaciation.
But I mean, the Sturtian glaciations in Australia cut through kilometers of stratigraphy. Locally, sure, yep. But I think I'd expect to see more of a trend towards, you know, having a range of values that span, say, the Burra group normal positive carbon isotope values into
The other point I would make is that I don't think that you should take, okay, so let me grant you, for sake of argument, that this is authigenic dolomite. I don't think you should assume that that it represents ambient seawater, because these ice margin, these grounding line deposits, of course, represent a mixing zone between seawater and subglacial meltwater. And so those subglacial meltwaters may be charged with alkalinity. And so, but the isotopic and chemical compositions that they represent should not be taken as a proxy for the glacial seawater.
Yeah, so again, that's an interesting point. So I think that there potentially is some influence of this alkalinity input via meltwaters, but you see these dolomites in a range of glacial marine environments. You see them, in fact, in intervals where there's no evidence of glaciation for hundreds of meters of stratigraphy. In bedded dolomites, you see them in tills, you see them in, in proximal and ice contact environments as well. But I think the range, the spectrum here of environments that they're precipitating in suggests to me that it's not a local condition associated with the ice shelves directly. It's a sort of feature of this Neoproterozoic seawater.
But the grounding lines are where these deposits occur.
Yeah, so some of the units in Australia, for example, are at the grounding line, but some of them are quite distal from the grounding line.
Okay, is that
Over to you, Greg.
stopping?
Okay, thanks.
Yeah, maybe you guys can
I
email
was going
each
to
other
take
or
a
something.
question.
I think Greg is next. So
Yeah,
Go
can you
ahead, Greg.
remind me, what units did you find the dolomite replacing quartz?
It's in all of those 6 carbonate units. So
In all of them? What in the Yankananina and in the Waring dolomite? And
yeah, on those big unconformities. Yeah, I don't think we
Sturtian
actually looked.
carbonate and in the Knuckalina as well?
In all of the ones that I talked about, maybe with the exception of the Waring, where I haven't looked at the SEM. Yeah, we looked certainly in the unconformities in the Mount Lyndhurst area. We looked a lot at those rocks.
Well, why I suddenly perked up was there is a place in nature where silicate grains are regularly replaced by carbonate, and it's in soils, in calcic horizons of soils.
Yeah,
They are always replacive. As you know, I think there are paleosols in the Knuckalina and other levels in that sequence. How do you rule out paleosols? I mean, that kind of observation of silicate replaced by carbonate is routine, and we do have dolomitic pedogenic carbonate, a lot of it actually.
Yeah, I think the paleosol idea doesn't really apply to these units. This is a marine sequence. These are basinal shales, Tapper Hill, for example. So is a kilometers thick basinal shale unit all through the basin. It's obviously quite deep water. There's really no evidence, I'd say, in a lot of these units for, I know that you think differently, but I would suggest from the sedimentology that I've seen, I don't think there's any evidence for paleosol conditions. But I do grant you that those conditions that you suggest are certainly something that can happen in soils. But I guess I'd probably say that they're happening more in marine settings in the units that I've looked at.
It just takes one paleosol in a marine sequence to make it non-marine.
Yeah, I guess so. Max is commenting there that there's also drop stones. There's drop stones in some of these sequences which couldn't be,
The reason why I went into this business about the coarsening upwards is, yes, that's climbing translatant cross stratification, which is an aeolian bed form. I think the so-called teepee structures are not teepees, but tents, and they are linear dunes downstream from thufa mounds, which create the initial disruption of the bedding plane. I think there's quite a number of aeolian and pedogenic features in some of these rocks.
Yeah, I guess you'd have to,
sure, but not all of it, I don't think.
Yeah, thanks for your comment. I think
the teepees are linear and parallel, so they're certainly not due to isotropic expansion like Kendall and Warren teepees.
Yes. And then the negative carbon isotopes and the correlation between carbon and oxygen. These are really not marine signatures.
I think these are, as I say, quite common marine signatures. You see these in the Flinders Ranges basin, the carbon isotope record. the stratigraphy is all suggestive of in most cases, open marine conditions. These big basinal shales, the dropstone shales that Max has pointed out, these are features in my mind of marine, certainly an open marine, very large open basin. This is a 14-kilometre thick sequence. I think for it to be paleosols, for hundreds of meters of stratigraphy would be very unlikely.
With few exceptions, they grade upwards into deeper water marine sequences.
Yeah, there's a soil across the whole North American continent. It's very extensive.
Greg, it's called macro stratigraphy.
Uh,
And it's called, looking at more than one outcrop.
Very good.
Looking at
Yes.
the whole.
I'm going to delve into your papers about that replacement. That's a really nice point. That you.
Oh, that's common. Dolomite is voracious.
The best mineral out there.
Hmm.
All right, cool. Max had a point that I'm just going to read out it, but that came out in that there are also drop stones present in some of the units. Yeah. So just for anybody watching on YouTube. Other than that, does anybody else have anything they'd like to say, bring up? Go ahead and just unmute yourself. I'll give a few seconds for that. All right, Ashleigh, it seems everybody was very content, and that was some really fun discussion. So yeah, thanks for that. It was great to have you.
Thanks very much. Thanks, everyone. Thanks for your questions. That was really good.
Thanks, Ash.
Thanks, Paul.
I also noticed, and I wanted to note, Ashleigh, that I think there were probably plenty of other people who would have been here to hear you, and I'm sure they're going to be watching on YouTube, but they're right now up the street in Ventura at the Gordon Geobiology Conference. So I'm sure if you guys are watching the video and you got this far, go if you want to ask Ashleigh a question, probably send her an email. So all right, Ashleigh and everybody, take care and see you all soon.
Thanks very much. Thanks, Alex.